All right, this is the second part to the severe weather sort of discussion here, and I kind of just went over some brief, some just kind of on the surface sort of things that revolve around severe weather. But now I'm going to really talk about the different sort of tools we use, different things we use, and how we use them and how they're used in our forecast. So our instability that I had mentioned in the very beginning is going to be our CAPE. It's called CAPE and it means our convective available potential energy. Well, what is this? It is, and this is directly from the National Weather Service, it is the amount of fuel available to a developing thunderstorm. So CAPE is the amount of fuel available to a developing thunderstorm. And it describes it as the instability of the atmosphere. Um, It provides an approximation of updraft strength within a thunderstorm. A higher value of CAPE means the atmosphere is more unstable and would therefore produce a stronger updraft. Well, what does a stronger updraft mean? Well, let's kind of go back to what I said about rising air, the air parcels. For air parcels to rise, you need energy to make them rise. So this energy to make air parcels rise is called CAPE. This is the energy used to make air parcels rise. And when these air parcels, interact with this CAPE, it makes them rise. Now, there is a case where sometimes there's an amount of energy that needs to happen first before a parcel can really take off. And I will explain that in a second. But usually, higher amount of CAPE, the stronger that air parcel is going to rise up in our atmosphere. And the more, billions of air parcels, you're going to create a huge updraft, a huge place of rising air in a thunderstorm. So it's very important to look at CAPE values, in forecasting severe weather. Anything really over 1,000 joules per kilogram, and that's the unit for CAPE, is going to be at least somewhat suitable. You want more, of course, but that's going to at least be enough to kind of create enough rising air. But the CAPE is calculated by determining the area between the environmental temperature trace and the trajectory of an air particle that is forced upwards on an atmospheric sounding. And atmospheric sounding we'll get into in a second, but essentially, um, air particle that's forced upwards, and CAPE is the area between the actual temperature line and the trajectory of an air parcel, that line, which try my best to I will try my best to explain, which it might be easier to I might do that now. So give me 1 second here. And I'm going to try to make this better here. Uh, okay. So let's let's talk about this real quick. So CAPE is calculated by determining the area between the environmental temperature trace, but essentially the environmental temperature and the trajectory of an air parcel. So the environmental temperature and the air parcel. Okay. Well, what is that on a environmental sounding? This on the left here This right here is our environmental sounding. This is a vertical representation of what's going on directly above us in the atmosphere. Okay, kind of a little hard to see, but you see this straight red line here. This red line, that is our environmental temperature. Essentially, that is just our temperature. All right. Well, what is our air parcel? Our air parcel is this white line, right, right here. That is our air parcel. This isn't really a great. There we go. This is a little better. But yeah, you see, our air parcel is this white dashed line. So our cape is anywhere between this environmental temperature and the parcel. So in this sounding here, very bad, very bad example, but here's our environmental temperature on the left, this red line, and here's our air parcel on the right. And our cape is in between these two on a sounding. So right in here, we have just a little bit of cape, just a little bit of cape. And I know that because, well, it's right there. There's 106, which isn't a lot at all, but that's how you see it in a sounding. Um, kind of confusing, I know, but I try my best to explain that. If you have any questions, like, of course, let me know. So I had mentioned that sometimes an air parcel needs a certain amount of energy to start rising. Okay. This is called sin. Sin. This is the negative part of the sounding. And of course, the sounding is this vertical structure of the atmosphere of a particular location. Uh, it's a vertical representation. The more sin you have is equals the less likely for storms. The more energy a parcel needs to rise is limiting, it's using that energy for that parcel to even start rising instead of creating thunderstorms. So it's like wasting the energy essentially. That parcel needs so much amount of energy to even start rising to get warmer than the environmental temperature, your air temperature, that energy is being wasted warming those parcels up enough to start rising that by the time they even rise, that sometimes it's too late because the daylight and the daylight heating is just gone. Sometimes that's not the case, but most sometimes it is. And the more sin you have, so the more energy that parcel needs to rise, the less likely you're going to have storms because this was wasting that energy essentially. And sin is this blue part. Um, and I'll just show it on here again. So this is better. I should have just showed it on this one, but you have your red line here, which is your environmental temperature. Your white dash line is your air parcel. Remember, in between your environmental temperature on the left and air parcel on the right is your cape. So this is a lot of cape right here. But let's reverse that. Let's say your air parcel is on the left. You see this white dash line, you follow it. Okay, look, now it's on the left of the red solid line, excuse me. That means our air parcel is colder than our air temperature. Well, that means that this small area right here is our sin. Now, this very small bit of sin is usually not going to be enough to cause issues. This can be the parcel can have enough energy within an hour or two to really overcome that. I mean, of course, it depends. There's other variables, but this in between your air parcel on the left and your environmental temperature on the right, that is your sin. So this little area here, this is your cape. Um, I don't know, hard to explain, and I got so much more to go. But yeah, here's our mixed layer cape, and I'm just going to kind of briefly go over these, just introduce you to these sort of things. Cape is very important. I kind of wanted to spend quite a bit of time on that, but I'm just going to quickly, briefly go over these. You could research these more um, if you'd like. But this is mixed layer cape. It's widely used. It's widely accepted. It's a mean potential energy conditions available to parcels of air located in the lowest 100 millibars when lifted to the level of free condensation. So essentially, here the blue is our sin, or yeah, our sin. Um, the deeper blues you have is the more energy those parcels need to overcome. So the more sin we have. These red lines here is our that's our cape, our mixed layer cape. So what we like to look at when we're forecasting for severe weather is, are there areas of high level cape and low level sin and low areas of sin? Well, here we go. Look in south central Kansas and north central Oklahoma. There's a lot of cape, 3,500 joules per kilogram. That's a lot of cape to work with. But also look, there's no sin, there's no blue around there. So if I were forecasting just based on this image alone, I'd say this area right here would be the best area for severe weather. Um, there's also most unstable cape. It's just the total amount of potential energy available to the most unstable parcel of air found. It's just another way to look at cape values and the data. Also LPL, which is the lifted parcel level. This is the height of the most unstable parcel, how high that parcel is going. Um, it identifies areas where the largest cape is elevated. And here's an example of that. You can see our cape and the yellows and oranges, and then our lifted parcel level and the red lines. Right here, just kind of what that map looks like. This is also important here. Our mixed layer cape, 0 to 3 kilometers. Um, it's cape confined in the lowest 3 kilometers of the atmosphere. Very important to look at. It's believed to be a quick acceleration of parcels, um, increasing the ability of those parcels to tilt and stretch horizontal, to stretch the horizontal vorticity. Um, so very important when we're looking at severe weather. The higher this value is, the higher you're going to have that stretching in the horizontal uh, vorticity plane, which just increases the rotation and updrafts and within your thunderstorms. So very very important to look at. The more energy you have on that surface, the more movement you're going to have essentially. But in order to generate these high values of CAPE, our LCL and LFC must be low. And what is that? LCL, LFC. LCL is our lifted condensation level, height at which a parcel becomes saturated. Our LFC is our level at which a lifted parcel begins to go upwards. It begins to rise to the equilibrium level. Okay, well, what is that? And I'll explain it. But give me 1 second. Level at which it's also the level at which parcel becomes warmer than the environmental temperature after reaching the LCL. So the LCL is when the parcel becomes saturated. It becomes the same as the environmental temperature. As soon as it begins to become higher than the environmental temperature, it enters the level of free convection and rises up. And then tornadoes are more likely with a lower LFC height on a sounding. Your lower LFC height, um, lower the LFC height essentially means the more cape, the more instability you're going to have because that parcel is able to rise faster and it's able to rise more and higher in the atmosphere. this is kind of what those maps look like. Um, just kind of introducing what these maps look like. You can um, view all these maps on the mesoscale analysis data page of the NOAA National Weather Service website. It's all free. It's all public information. And here is I just wanted to explain um, LCL, LFC, and the equilibrium level on the sounding. We see here our LCL is where our air temperature is the same as our dew point. I think I said that, right, the air parcel is the same as our temperature. Um, I'm wrong, sorry, but I meant our air temperature becomes the same as our dew point. Um, that's the area of full saturation. Our LFC is where that air parcel. This is what I was talking about. Our LFC is where our air parcel finally becomes the same temperature as our air temperature. And when it goes higher, when it reaches higher than our air temperature, here's our cape. But as soon as it cools down, when that parcel cools down back to the air temperature, that enters our equilibrium level, which is right here. So that's just a good way to look at that. We have our lifted index or our surface-based lifted index. Um, Larger negative values just essentially means more instability. Um, it's just the comparison of a surface-based partial raised adiabatically to the 500 millibar to the environmental temperature at 500 millibar. This is what this looks like. And you can see the higher the negative values, the more instability. Again, just kind of briefly going over that. Very important though is our shear. We have two types of shear. We have our 0 to 1 kilometer shear and then our 0 to 6 kilometer shear. Our 0 to 1 is the difference between winds at surface and the winds at 1 kilometer above ground level. Anything around 10 to 15 knots or higher favors tornadic supercells. 0 to 6 kilometers. It's the same thing. It's between the surface and 6 kilometers. But um, you get a better idea of the change of wind for this height, though. So it's very important to look at higher up in the atmosphere to 6 kilometers. Anything over 35 to 40 knots or greater, and the shear vectors favor supercells. And you need turning at the surface and the mid levels for tornadic supercells. So you need turning at the 0 to 1 kilometer level, and you need turning at the 0 to 6 kilometer level. You need turning at the surface and the mid levels for tornadic supercells. You need high shear. You need favorable shear for tornadic supercells in severe weather, just in general. And these are what these maps look like. Very, sort of a little bit easier to read, but definitely definitely very important. So additionally, something else some people use is the effective bulk shear. It takes the surface base 0 to 6 kilometer shear. However, it takes account for storm depth. It's designed to see elevated or surface-based supercell environments. And what that is elevated environments is unstable air rises high in the atmosphere, above a stable air closer to the surface. The surface environment, unstable air near the surface, is forced to rise closer to the surface. It's that air parcel rising, those parcels rising are forced to spread out closer to the surface essentially. Um, and anything around 25 to 40 knots or greater favors supercells. Important to know here is the storm relative helicity. Um, 0 to 1 kilometer storm relative helicity can be known as, but it's the measure of the potential for cyclonic updraft rotation and right moving supercells. Larger values of 0 to 3 kilometer SRH of more than 250 meters squared by second squared, and 0 to 1 kilometer SRH greater than 100 meters squared over second squared favor an increased threat of tornadoes. Um, and like I said, there's also 0 to 3 kilometer SRH with the 0 to 1. It's very important to look at both. Um, the higher these numbers, higher than 250, higher than 100, um, essentially means the faster these updrafts are rotating. So the faster they're rotating, the more violently they're rotating, you might have a better chance for more violent tornadoes. That's kind of what a map looks like, um, in that sense. Another tool here is our supercell composite parameter. It's just a multiple ingredient composite index and includes storm relative helicity, the most unstable cape, and the effective bulk wind difference. I'm just mentioning this because it's not very great. It's not very used. I don't really use it too much. I don't really look at it too much. Every now and then I will. But people will throw this around, and it's just important to realize that, um, yeah, you can look at it. Yeah, it has its benefits, but usually it's not great. More used though is the significant tornado parameter. It's still not amazing, but still it's a multiple ingredient index, and it includes the effective bulk wind difference, the effective storm relative helicity, the 100 millibar mean parcel cape, the 100 millibar mean parcel sin, and the 100 millibar mean parcel LCL height. So it takes in a lot more. It's a better thing to use in my opinion. Still, you don't want to go off of it. You don't want to base your forecast solely off this. That's not the correct thing to do. It's very interesting to look at. It's very cool to look at, and it can be used to maybe back up your forecast, maybe to see if you're on the right track. Or, sometimes it's wrong. Sometimes models are just wrong in general, but sometimes it's just used as maybe just a good little baseline, um, not to solely base your forecast off of, but just to have a decent idea of what's going on. But a majority of significant tornadoes have been associated with a STP value greater than 1 within an hour of tornado occurrence. This is kind of what this looks like. We have our mixed layer sin, and then we have our significant tornado parameter, the orange circles. And real quick, a tool that we use is a hodograph, and it's a visualization of shear in the atmosphere. Strong shear is directly correlated to storm organization, kind of like what I mentioned. It can be used to see what type of thunderstorms is likely. Supercell, multicell, and pulse storms. Supercell is your rotating updraft storms. Multicell is your like cell clusters. Um, we see these a lot in the Ohio Valley, multicell sort of systems, and pulse storms. Sometimes we'll see pulse storms too. But a lot of the times we'll see our multi-cell systems. But photographs can be used to actually see that in their atmosphere, because our shear can tell us that. So supercell, what photograph, supercell wise, it's strong veering of wind in the low levels, extending into the mid levels. Wind speed is usually greater than 20 knots in the low levels, and preferably greater than 100 knots from uh, 500 to 300 millibars. The stronger the wind, generally the more favorable. Wind speeds very high in the upper levels, greater than 100 knots. The higher the better. essentially the higher the winds, um, the more turning you're going to have, and um, that's what you need for a supercell. It curves sharply with height, almost looks like a fish hook, but and it goes in a clockwise direction as well. The winds will go in a clockwise direction. So, um, not a great example of a supercell photograph, but I just kind of want to show you where a photograph even is. So on the left here we have our sounding. Sorry, we have our sounding on the left, but on the right here, on the top right, this is our photograph. And we can see our line here. But usually in a supercell, this line would be kind of like this, kind of like a fish hook, kind of like that maybe. But this is what it looks like. It's kind of want to get you familiar with what it looks like. But very important to use when looking at severe weather. Yeah. So here is a clockwise photograph or a fishhook photograph, and you can see this kind of like the little fishhook um, formation. This usually means it has greater turning, higher speed, higher curvature shear. Um, if you want if you want tornadic supercells, which I don't know why you would, but if you're out chasing or anything, you'd want something to look like this. Anything that looks like this, um, usually not a good sign. Not a good sign. And here's just some pictures, kind of just to see what a supercell looks like here. So we have our a supercell essentially is just a cold. It's like a little miniature cold, low pressure system. Um, we have our cold air rushing out from the top here, and then you have it rushing out from behind. In a supercell, though, you have inflow. You get this little warm notch here where it draws in the warm air. It's right here. You can kind of see here's your rotating updraft here. The highest part of your thunderstorm is your rotating updraft. That's where your tornado will be, but that's also where your inflow is being brought in the most. Your inflow is going to be brought in the most in the most tornadic area of your supercell. So very cool kind of diagrams. You can look at these, but we end this here. If you have any questions, let me know. Long video, I'm sorry. But with severe weather season, I felt like I needed to just throw out some tools, throw out some basic concepts of severe weather. I know I didn't explain them probably as well as I could, but if you have any questions, just let me know.